Hi students, in today's video class, we are going to discuss a very important topic in the chapter nuclear transformations, and that is alpha decay. Now what is alpha decay? It is the radioactive decay process in which a heavy unstable nucleus disintegrates to become a light stable nucleus by emitting alpha particles. That is, nuclei with mass number 210 or more, that is, nuclei having nucleons, number of nucleons equal to 210 or more, are so large that the short range nuclear forces are not able to hold the nucleons together, or they are not able to counterbalance or oppose the or overcome the mutual repulsion of the protons in such nuclei. So these nuclei undergo alpha decay to reduce their size and gain stability. അതായത് ഒരു ന്യൂക്ലിയയുടെ മാസ് നമ്പർ 210 അല്ലെ അധികമോ ആയാൽ 210 അല്ലെങ്കിൽ അതിൽ അധികമായാൽ the number of nucleons will be so large that the proton repulsion will be very high, so that the strong nuclear force will not be able to balance these repulsive forces. So the repulsive force will be greater than the strong nuclear force, and the nuclei will become highly unstable. So the nuclei will undergo alpha decay to reduce the size and gain stability. So let us see how that reduction in size take place. So this is how the alpha decay takes place. So ZXA is our parent nuclei, Z minus 2, YA minus 4 is the daughter nuclei, and here an alpha particle is emitted. As you all know, alpha particle is a helium nuclei, so H2He4. So when the alpha particle is emitted, the parent nucleus exchanges to the daughter nucleus Y, and the atomic number of the parent nucleus reduces by 2 and its mass number reduces by 4. That means the size of the particle is reducing, and in this process, the particle, the nuclei gains stability. Our next question is, why are alpha particles emitted from the nucleus rather than protons or 2He4 nuclei? So, why are we particular, or why is it particularly that the alpha particles are emitted from the nucleus other than particles like these? Even if a proton is emitted or a 2He3 nucleus is emitted, then also the size of the nucleus will reduce. But these particles are not emitted. Instead, it is particular that the alpha particles are being emitted. So what's the reason for that? എന്തുകൊണ്ടാണ് ആൽഫ പാർട്ടിക്കിൾ മാത്രം ന്യൂക്ലിയസിൽ നിന്ന് എമിറ്റ് ചെയ്യപ്പെടുന്നത്? എന്തുകൊണ്ട് പ്രോട്ടോണോ അല്ലെങ്കിൽ 2He3 എന്നൊക്കെ പറയുന്ന ന്യൂക്ലിയൈകളൊന്നും ഒരു ന്യൂക്ലിയസിൽ നിന്ന് എമിറ്റ് ചെയ്യപ്പെടാത്തത്? ഇവരെ എമിറ്റ് ചെയ്താലും ന്യൂക്ലിയസിന്റെ സൈസ് കുറയ്ക്കാവുന്നതേ ഉള്ളൂ. അപ്പൊ എന്തുകൊണ്ടാണ് particularly alpha particle തന്നെ emit ചെയ്യപ്പെടുന്നത്? To answer this question, the disintegration energy is calculated in each case. Now, what is disintegration energy? Disintegration energy Q is equal to Mi minus Mf minus Mx into C square. Mi is the mass of the initial nucleus, that is the parent nucleus. Mf is the mass of the final nucleus or the daughter nucleus, and Mx is the mass of the emitted particle, whether it is alpha or proton or 2He3 nuclei, etc. Now, from the calculations of Q, we find that alpha particle emission is an energetically possible process, whereas the other decay modes need energy to be supplied to the nucleus. That is, alpha decay is accompanied by the release of 5.4 MeV of energy, while 6.1 MeV need to be supplied for a proton to be emitted, and 9.6 MeV of energy need to be supplied for 2He3 nucleus to be emitted. So they are energetically unfavorable. These emissions are energetically unfavorable, whereas alpha decay is an energetically possible and favorable decay mode. So it is alpha decay that takes place to reduce the size of the nucleus. Now, what is the relationship between the kinetic energy of the alpha particle and this disintegration energy? kinetic energy of alpha is equal to A minus 4 by 4 into Q. Since A is always very large, so this quantity is 210 minus 4 by 210, that is nearly, that is 206 by 210. So it's nearly equal to 1. So almost all of the disintegration energy is getting converted to the kinetic energy of the alpha particle. So they remain nearly the same. Next, we come to the important essay, first important essay from this chapter, that is the tunnel theory of alpha decay or Gamow's theory of alpha decay. Now, what is this tunnel theory? In alpha decay, an alpha particle have to escape from the nucleus. Now, alpha particles usually have energies in the range 4 to 9 MeV, whereas the potential barrier posed to the alpha particle by the nucleus is about 25 MeV. Classically, an alpha particle with an energy lower than that of the potential barrier will never be able to escape from the nucleus. But quantum mechanically, there is a very small but finite probability for the alpha particle to surmount the barrier and escape from the nucleus. So, based on this, the theory of alpha decay was put forward by Gamow, Gurney, and Condon in 1928. And this theory is called the tunnel theory of alpha decay. അതായത് ആൽഫ ഡീകെ എന്ന് വെച്ചാൽ ഒരു ആൽഫ പാർട്ടിക്കിൾ ന്യൂക്ലിയസിൽ നിന്ന് പുറത്തു വരണം. യൂഷ്വലി ദി എനർജി ഓഫ് ആൽഫ പാർട്ടിക്കിൾസ് എന്ന് പറയുന്നത് ഇറ്റ് ഈസ് അബൌട്ട് 4 to 9 MeV ഓഫ് എനർജി. എന്നാൽ ഒരു ന്യൂക്ലിയസ് ഒരു ആൽഫ പാർട്ടിക്കിളിനെ പ്രസന്റ് ചെയ്യുന്ന പൊട്ടൻഷ്യൽ ബാരിയർ എന്ന് വെച്ചാൽ, പ്രതിരോധം എന്ന് വെച്ചാൽ ഇറ്റ് ഈസ് അബൌട്ട് 25 MeV ഓഫ് എനർജി. ഇത്രയും വലിയ ഒരു പൊട്ടൻഷ്യൽ ബാരിയറിനെ വെറും 4 അല്ലെങ്കിൽ 4 മുതൽ 9 വരെ MeV വരെ എനർജി ഉള്ള ഒരു ആൽഫ പാർട്ടിക്കിളിന് ക്ലാസിക്കലി പറയുകയാണെങ്കിൽ ഒരിക്കലും മറികടക്കാൻ സാധിക്കില്ല. അങ്ങനെ ന്യൂക്ലിയസിന്റെ പുറത്തു വരാനും പാടില്ല. എന്നാൽ ക്വാണ്ടം മെക്കാനിക്സ് പ്രകാരം എനർജി കുറഞ്ഞ പാർട്ടിക്കിൾസിനും ഒരു പൊട്ടൻഷ്യൽ ബാരിയറിനെ, അതിനേക്കാൾ എത്രയോ മടങ്ങ് എനർജി കൂടുതലുള്ള ഒരു പൊട്ടൻഷ്യൽ ബാരിയറിൽ കൂടി പുറത്തേക്ക് കടക്കാൻ വളരെ 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 ചെറുതാണെങ്കിലും ഒരു നോൺ സീറോ പ്രോബബിലിറ്റി ഉണ്ട്. അപ്പോൾ ഈ ക്വാണ്ടം മെക്കാനിക്കൽ തിയറിയെ ബേസ് ചെയ്തുകൊണ്ടാണ് ആൽഫ ഡീക്കേന്റെ എക്സ്പ്ലനേഷൻ ഗമൗ മുന്നോട്ട് വെച്ചത്. So the basic notions of this theory are: an alpha particle may exist as an entity within a heavy nucleus. So the alpha particle is existing as a separate entity within the heavy nucleus. അത് ഒറ്റയ്ക്ക് ഈ ന്യൂക്ലിയസിന്റെ ഉള്ളിൽ ആൽഫ പാർട്ടിക്കിൾ ആയി തന്നെ നിൽക്കുന്നു. ആൽഫ പാർട്ടിക്കിൾ is in constant motion and is held inside the nucleus by the potential barrier. The alpha particle is constantly moving inside the nucleus and it's held by the potential barrier inside the nucleus. Now there is a small but finite likelihood for the particle, so that the particle may tunnel through the barrier each time it hits the or collides with the barrier wall. So the alpha particle is continuously moving inside the potential barrier and it's hitting the walls of this barrier. Or during each collision, or it collides a number of times, and during each collision there is a very very small but a definite likelihood or a definite or finite probability for the particle to escape or tunnel through the barrier. Now the potential energy of U of an alpha particle as a function of its distance from the center of the heavy nucleus is shown here. So this is how it is. This is the nuclear radius R0. Now my alpha particle is trapped here, and this is the potential barrier posed by the nucleus. Now the speciality of this potential barrier is that its strength reduces with distance. So it is a varying potential barrier. Okay, it's not a potential barrier of uh, I mean, you have already learned in your quantum mechanics class that about potential barrier of finite height. Okay, when a particle, what happens when a particle is trapped inside a rectangular potential barrier is already known to you. But here, if alpha particle is encountering, the alpha particle inside the nucleus is not encountering a potential barrier or rectangular potential barrier, but a barrier of varying height. So the height is varying with distance. So at R0, the height of the potential barrier is maximum, and as you move away from the nuclear radius, the height of the potential barrier goes on decreasing. Okay, so if this is the energy of the alpha particle, what we see is that this we have drawn the alpha particle wave function here. It is usually the wave function is confined because the particle is confined inside the nucleus, but there is a small and finite probability for the particle to tunnel through this barrier and escape out. This is the energy of the alpha particle. So once it crosses this region, it is free and it comes out of the nucleus. Okay. So the alpha particle is contained inside the nucleus. So E represents the energy of the alpha particle. R0 represents the nuclear radius, and this represents the potential barrier. This one, the potential barrier of varying height. Okay, so once the uh, alpha particle is able to overcome or surmount this height, then it will come out of the nucleus. Okay, so now we are going to begin our derivation. The decay probability per unit time, that is lambda, our decay constant, is given by nu into capital P, where nu is the collision frequency, that is the number of times the alpha particle hits the collides with the barrier posed by the nucleus, and P is the probability that the particle will be transmitted through the barrier during each collision. P is the probability that the particle will be transmitted through the barrier during each collision, and nu gives you the total number of collisions, so that the product of these two will give you the decay probability per unit time. Suppose that only one alpha particle exists in the nucleus and it moves back and forth along the nuclear diameter. So if R0 is the nuclear radius, then the 2R0 will give you the nuclear diameter. And the alpha particle is moving back and front or back and forth along the nuclear radius. Then the collision frequency is given by, we know time is given by distance by velocity. So frequency is given by velocity by distance. If v is the velocity of alpha particle and distance traveled is along the nuclear diameter, so 2r0. So collision frequency nu that we used here is given by nu is equal to v by r0. So our decay constant, as you know, v is nearly equal to 1/10 the velocity of light, that is 2 into 10 raised to 7 meter per second. R0, 1 Fermi, or nearly 10 raised to minus 14. So collision frequency is nearly 10 raised to 21 per second. So 10 raised to 21 collisions it is making per second. So lambda is equal to, I've replaced nu with v by 2r0 into p. Hence, the transmission probability of the alpha particle uh, across a barrier of constant height u and barrier width L is given by, this you have learned in your quantum physics quantum mechanics. That is, if a particle is encountering a rectangular potential barrier of height u and width L, its probability of transmission, അതായത് ഒരു ഇത് നമ്മൾ ഫിഫ്ത്ത് സെമിസ്റ്റർ ക്വാണ്ടം മെക്കാനിക്സിൽ പഠിച്ചതാണ്. അതായത് ഒരു പാർട്ടിക്കിൾ വന്ന് ഒരു റെക്ടാങ്കുലർ ബാരിയറിനെ ഹിറ്റ് ചെയ്യുകയാണെങ്കിൽ, റെക്ടാങ്കുലർ ബാരിയർ ഹാവിംഗ് ഹൈറ്റ് h ആൻഡ് വിഡ്ത്ത് l, L വിഡ്ത്തും ഹൈറ്റ് എച്ചും ഉള്ള ഒരു റെക്ടാങ്കുലർ ബാരിയറിനെ വന്ന് ഒരു പാർട്ടിക്കിൾ ഇടിക്കുകയാണെങ്കിൽ പാർട്ടിക്കിളിന്റെ ഹൈറ്റ് എനർജി കുറവാണെങ്കിൽ പോലും യുവിനേക്കാൾ ഈ ബാരിയറിന്റെ ഹൈറ്റിനേക്കാൾ കുറവാണെങ്കിലും അതിന് ഈ ബാരിയറിനെ മറികടക്കാനുള്ള ഒരു ട്രാൻസ്മിഷൻ പ്രോബബിലിറ്റി സാധ്യത അവിടെ ഉണ്ട്. And that is given by T is equal to e raised to minus 2k2L. That transmission probability, you have learned it as T is equal to e raised to minus 2k2L, where k2 is the wave number inside the barrier given by 2m u minus e by h cross. I'm not explaining to you how this has come because you have already learned it in your quantum mechanics class. H cross k is momentum, and you have found out the momentum here, root of 2m u minus e. The expression T, this expression for transmission probability is obtained for or derived for the rectangular potential barrier. But here the alpha particle inside the nucleus is faced with a barrier of varying height. That is, usually a rectangular potential barrier should be like this. That is, it should come like this, and here there must be a rectangle. But here instead of that, it is here a varying potential barrier is there, not a rectangular one, but a varying potential barrier. So the equation for transmission probability need to be modified. So what we do is, T is the transmission probability for rectangular barrier. So T is equal to e raised to minus 2k2L. Log of that is equal to ln T is equal to minus 2k2L. So ln T, what we do is, the width is not a constant here. Here for a rectangular barrier, width of the barrier is L. Width is L. It is a constant. But in this case, the width is varying. So we change it to ln T is equal to minus 2 k2r dr. That is, the wave number changes for every dr, and you find the product of that and integrate it. So minus 2 integral k to r dr. That is, you are simply doing minus 2 k into L. K2 into dr. For every small dr, you are determining K2 and multiplying them. And you integrate this over R0 to R. That is, from where to where does the potential barrier vary? The potential barrier varies from R0 to this R. After that, the energy of the barrier is less than that of the alpha particle. This is the E represents the energy of the alpha particle, and after R, the energy of the barrier is less than that of the alpha particle. So the particle will surely come out. So we have to bother only about the transmission probability from between R0 to R. So we are integrating it. Integrating the transmission probability within the limits R0 to R. Okay, so in this case, where R0 is the radius of the nucleus and R is the distance where the energy of the particle becomes equal to the energy of the potential barrier, that you can see here. That is, once that distance is reached, the alpha particle simply comes out of the nucleus. So R is the point where the energy of the the energy of the alpha particle becomes equal to the energy of the potential barrier, and once it reaches here, it will come out of the alpha particle. I mean, it comes out of the nucleus. Now, for the alpha particle to escape from the nucleus, E must be greater than U. For small r greater than r. Here, the electrical potential energy of the alpha particle at a distance small r from the center is given by U is equal to 1 by 4 pi epsilon 0. You know the potential energy between two charged bodies is given by 1 by 4 pi epsilon 0 q1 q2 by r. Here q1 is the atomic number of the nucleus into its charge into that of the alpha particle, 2 into E, the next charge particle. So it is 1 by 4 pi epsilon 0 into Q1 എന്ന് പറയുന്നത് ആ ന്യൂക്ലിയസിന്റെ ചാർജ് ZD, Q2 എന്ന് പറയുന്ന ആൽഫ പാർട്ടിക്കിളിന്റെ ചാർജ് 2E, അത് രണ്ടും കൂടി മൾട്ടിപ്ലൈ ചെയ്താൽ നമുക്ക് 2 into Z into E square by small r എന്ന് കിട്ടും. And so our K2 can be replaced as root of 2m u minus e by h cross എന്നുള്ളത് u ന്റെ എക്സ്പ്രഷൻ നമുക്ക് കിട്ടി അതിനെ ഇതിൽ സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്യുന്നു 2m by h cross whole raised to half into 2z e square by 4 pi epsilon 0 r minus e the whole raised to half. What I simply did was I substituted for u here. Next, we know that when U is equal to E, when the energy of the barrier is equal to energy of alpha particle, that happens at a distance r equal to small r. So that E is equal to 2z E square by 4 pi epsilon 0 capital R. You replace small r by capital R, then you reach the point when, or you get that energy when the energy of the alpha particle is equal to that of the barrier. Now, what we do is we substitute that 2 here. What we do is you substitute for um, 2z e square by 4 pi epsilon 0 is substituted with, that is this term, 2z e square by 4 pi epsilon 0 is equal to E into R, capital E into R. So instead of this, I write here capital E into capital R so that I can take E common factor out from this. So my equation becomes K2 is equal to 2me by h cross square into capital R by small r minus 1, because I have taken this term is replaced from here by, see, 2z e square by 4 pi epsilon 0 will be equal to capital E into this r will be equal to this term. So that is replaced here. E I took common factor out so that it becomes K2 is equal to root of this constant into capital R by small r minus 1 the whole raised to half. Now I substitute this K2 value in the equation for transmission probability. Log T is equal to minus 2m e by h cross square the whole raised to half integral r0 to r. I replace the term with this. Okay. Now what we have to, we have got the answer. Just you have to do some mathematical adjustments to reach the final value for the transmission probability in this case. What we do is I substitute small r by capital R to be cos square phi. So that small r is equal to capital R cos square phi, and derivative of small r dr is equal to minus 2r cos phi sin phi d phi. That is all simple mathematics, and all these things are substituted here. So I just take, without the integral, I take this term capital R by small r minus 1 the whole raised to half dr, and I substitute these values here. ഈ വാല്യൂകളെല്ലാം ഞാൻ ഈ ഭാഗത്ത് ഇന്റഗ്രൽ ഇല്ലാതെ ആ ടേം മാത്രം എടുത്ത് അവിടെ സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്യുന്നു. So you can go through the mathematical steps. Simple trigonometric identities are used and we reach the value minus r into 1 minus cos 2 phi d phi. Okay. I've shown the detailed steps here. So I think it won't be difficult for you. If you have any doubts, you can contact. And after I get this answer, I come back to the integration and I integrate. Integral r0 to r capital R by small r minus 1 the whole raised to r, and that I am replacing it with this term. So minus r integral r0 to r 1 minus cos 2 phi d phi, and I integrate. So minus r integral phi minus sin 2 phi by 2 within the limits r0 to r. That is minus r into phi minus 2 sin phi cos phi r and r0. Now what I do is capital R by small r, you know it is cos square phi, our first assumption. So that sin square phi is equal to 1 minus cos square phi. So what is cos phi? It is root of capital R by small r by capital R into whole raised to half. And what is sin square phi? 1 minus cos square phi I replace from here, and then sin phi will be the root of this. So all those terms are replaced here, and then you apply the limits. So cos inverse phi is cos inverse r0 by r the whole raised to half minus cos phi, sin phi, cos phi, all are replaced from here. Okay, phi is cos inverse r0 by r root. Then cos phi is r0 by r the whole raised to half. Sin phi, that part also it is 1 minus r square by r the whole raised to half. And whatever we do here is the answer that you have obtained here is after applying the limits capital R and R0. Okay. So this is the answer that you get as a result of this integration. Now, the potential barrier is relatively wide. It is considered to be much wider than the nuclear radius. So what happens is R0 by R, capital R is much bigger than R0, so that this becomes a very small number. So we know that cos theta is equal to sin 90 minus theta. Now if this value, if this angle 90 minus theta, that angle is very small, then sin 90 minus theta is 90 minus theta. So cos inverse, we do some approximations here. Cos inverse R0 by R half is nearly equal to pi by 2 minus R0 by R the whole raised to half. And 1 minus r0 by r the whole raised to half is r0 by r is a very small value, so it's nearly equal to 1. So you make those substitutions here so that you get log t or natural logarithm of t to be of this form. Then we make the substitution for capital R as 2z square by 4 pi epsilon 0 capital E, because this R is not known to us. നമുക്കറിയില്ല ഈ പൊട്ടൻഷ്യൽ ബാരിയറിന്റെ വിഡ്ത്ത് എന്താണെന്ന്. നമുക്കറിയാവുന്ന ഏക സാധനം എനർജി ഓഫ് ദി ആൽഫ പാർട്ടിക്കിൾ ആണ്. അപ്പൊ അതിനെ ഉപയോഗിച്ച് നമുക്കറിയാവുന്ന സാധനങ്ങളാണ് അറ്റമിക് നമ്പർ ഓഫ് ദി പാരന്റ് ന്യൂക്ലിയർ, എനർജി ഓഫ് ദി ആൽഫ പാർട്ടിക്കിൾ. ഇതെല്ലാം ഉപയോഗിച്ച് നമ്മൾ ഈ ആൻസറിൽ സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്യുകയാണ്. So that you get natural logarithm of t. You get it in this manner after the substitution. Now here 4e by h cross m pi epsilon 0 root of m by pi epsilon 0 all are constant. So you get its value as 2.97, and all these terms are also constant. So you get it as 3.95. So that my equation becomes this. Okay, now what we do is, it is not the transmission probability that I need. I need the decay constant lambda. Lambda is equal to nu into t, that is v by 2 r0 into t. This was where we began our derivation from the probability of decay, the decay probability per unit time. And I am taking a logarithm of this so that it's equal to ln lambda, ln v by 2 r0 plus ln t. ln t we have already calculated. That I substitute here. Okay. So at the decay constant in alpha decay constant, or decay constant in alpha emission is given by, I took logarithm to the base 10, converted natural logarithm to logarithm to the base 10. So I get log lambda is equal to log v by 2 r0 plus, it is because of this change. You divide this by, to convert it into normal logarithm to the base 10, you multiply by 2.303. So to avoid that 2.303, you divide throughout all these terms by 2.303 so that you get these values. Okay, so this is the equation that Gamow derived. That is, decay probability or decay constant is given by this relation for an alpha decay. Now, we go to the experimental verification of this theory. That is, this theory put forward by Gamow matches with what is experimentally observed. So we are reaching that part. Now a graph of this log 10 versus z e raised to minus half is plotted here. A graph of log 10 versus z e raised to minus half is plotted for different radioactive nuclides, and you obtain a straight line which fitted with the experimental data, and it has a slope of minus 1.72. Okay. Now the intercept here, the y-intercept gives this value, these two terms, log v by 2r0 plus 1.29 z raised to half r0 raised to half. So that is given by the y-intercept, and this value of the y-intercept can be used to determine r0. Okay, nuclear radius. Now the nuclear radius calculated from this equation 1 by plotting the graph matched very well, or its order matched with that obtained from scattering experiments, which showed that Gamow's theory is very correct. Not only that, we know that the nuclei emitting very highly energetic alpha particles are short-lived, while those emitting low energy alpha particles are long-lived. This correlation between half-life and energy of alpha particle could also be provided from equation 1. Thus, the tunnel theory of alpha decay is in conformation with the experimentally obtained result, or matched very well with the experimentally observed result, proving that this theory is extremely true and the assumptions that we considered are all correct. Okay, so this is the tunnel theory of alpha decay. This is a very important essay, so I hope it's clear to all of you. If you have any doubts, please do contact. Thank you.